All right, you guys, so I don't know what order you did the videos in, although I think I put the horizontal asymptote videos first, but I think we've actually talked about this more. And we're going to talk about the vertical asymptotes of rational function. And remember, wait, I don't know if I can talk while I spell this. Totes. We are only working with rational functions in this case. So keep that in mind that when we're talking about a vertical asymptote for a rational function, because there's going to be vertical asymptotes for different types of functions, and I only want to talk about this one, functions. I'll stop talking so I can put this on. Functions, there's a C there. Okay, so keep in mind we're working with our rational functions. Rational functions are, of course, one polynomial divided by another polynomial. So going back to one of our basic fractions of polynomials, like if I just have 1 over x, and the vertical asymptote is where that function does not exist there, but it's going to get super, super close to it. So if I graphed 1 over x, if I graph over here, 1 divided by x, okay, this is what it looks like. And my vertical asymptote is going to be where y is 0 right here, right? The graph is gonna get super, super close. Where I put in, I'm sorry, x is equal to 0. I said y, I meant x. I'm sorry if you've been yelling at your computer for the past few seconds. But if I wish this had a highlighter, if you look at this, the graph will never exist where x is equal to 0, which is that y-intercept, that y-axis, but it's going to get super duper close to it. So watch, if I come over and I want to go out like that, maybe a little bit more in. Okay, and I move it. Look, it's going to get close to that axis, close. And look, it looks like it's right on top. And now let's go in. Nope, not on top. It's getting close. And you guys could do this an infinite amount of times, and it's never going to hit that y-axis. So if we go back to our notes, why is that? Why does it never hit that y-axis? Well, the y-axis is actually where x is equal to 0. That's how we define our y-axis. Because x is 0 all up and down the y-axis. Well, if x is 0, that's the only way you can get there. And so I knew that, and I want to put a 0 into the equation to find out where they cross, right? Well, once I do that, I'm dividing by 0 and the world explodes, right? You cannot divide by 0. Your denominator cannot be 0. And ladies and gentlemen, right there, that is how we find the vertical asymptotes of rational function. Remember, we're only talking about rational functions. And what we try to do is we force that denominator to be 0 because it can't be. We try to force it to be there. Once we realize what number is going to make it 0, that's our vertical asymptote. So our vertical asymptote in this situation is x equals 0 because that's what it can never be. It'll get close and close and close and close and close and close and close, but it'll never be there. Okay, but it's super easy for 1 over x, right? All we have to do is make x 0. What if we have a more difficult function? What if we have 2 over x squared minus 5x plus 6. What do we have this? How do we know what's going to make that denominator 0? Well, it's the same thing. I guess you could take that denominator. You could take the whole denominator, which is just a quadratic, and you can solve for 0 by using the quadratic formula. But this one actually looks pretty easy to factor. So let's just factor that denominator. Remember, we're looking for two numbers that add up to be -5 and multiply together to be +6. And I think that's going to be x add up to be -5. So it's going to be -2 times x minus 3, right? I think that works. So now, what's special about this one? This one's going to have like 2 places where we can make it 0. So it may have 2 vertical asymptotes, and that's okay. That's fine. It's just not going to exist there, right? Because if I make x positive 2, that's going to make the whole denominator 0, right? It's going to 0 it out from the rational 0 function. And here, if I make x positive 3, that's going to do the same thing. 3 minus 3 is 0 times this. The whole thing's going to blow up right there. So you know what? Let's go back into the calculator and see if that works. Let's see if there's a vertical asymptote at x equals positive 2 and at x equals positive 3. So we have 2 divided by x squared minus 5x plus 6. Let's see if we can make that explode. We have 2 divided by question mark 2 divided by, and I'm going to put it in parentheses, x squared, what was it, minus 5x plus 6. Okay, let's see what that looks like here. Let's find my 0. I kind of messed this picture up from the last time we were here, didn't I? Let's see. There it is. Here it is. So it was x equals positive 2, and it was x equals positive 3. So positive 2 is right here, right? And positive 3, it looks like, is right here because it's counting by 2's there. All right, so if I could draw lines up and down right there, this function would never, touch those 2 lines. I wish I could draw lines, but those points are going to have to be there. And then if we go up to the top and do the same thing, right? It works there too. And remember, if we went ahead and zoomed in, zoomed in, zoomed in until the cows came home, it would still never reach x equals positive 2 and x equals positive 3. Okay? There's one more thing I want to touch on, and that is sometimes some functions can have holes in them. And what do I mean by holes? Well, let me show you what I mean by holes. Let's go back to our notes. I'm going to go down a page, and we're going to talk about functions that have holes. And how is a hole different from a vertical asymptote? You're asking? Well, we're going to look into that. Functions with holes in them. Let's do an example here. What if the function I'm looking at is x minus 2 over x squared? What do I want this to be? Minus 4. Okay, and we want to make the denominator 0, and I wanted to factor it. What would that look like? And I know what you're thinking right now. You're thinking, Bingley, we don't need to factor it. We know if we put a 2 here, 2 squared is 4. 4 minus 4 is 0. The answer is 2 is going to make this function blow up. Well, that is one of them, but I want to factor it to show you something. So I have x minus 2 on the numerator, and if I factored it, I would get x minus 2 times x plus 2. Okay? And if I multiplied x minus 2 times x plus 2, I would get x squared minus 4. But check it, you guys. I have exactly x minus 2 on the numerator. So I could actually, if I wanted to reduce this, cross those off and cancel it out. And now I just have 1 over x plus 2. So the only number that is going to blow this up is x equals negative 2. But we know from this original one, before we canceled that out, a positive 2 here would also make it 0. So what has happened to it? Well, x equals negative 2 is definitely a vertical asymptote. X equals positive 2 is what we call a whole or an extraneous solution, okay? I hope I spelled that right, extraneous solution. Because it's a solution that can be there when we look at it here where I've circled, but it goes away when I look at it over here after I've canceled something out. So let's go ahead and look at it on the graph. Okay, let's put this into the graph. And I'm going to pause it here because I'm running out of time. So when I start recording again, you'll magically see a graph in front of you. All right, you guys, so here is the equation that we graphed, the rational function that we graphed. And as you can see, our negative 2, that is definitely where our vertical asymptote is, right? Right here. But here, it actually looks like our function exists here, which is why you can't always trust what you see, because you know if we put 2 into the equation, it would explode, it would blow up because it would give us a 0 on the denominator. So that's why we call that answer an extraneous answer, okay, because it's still not there. If you looked in a table, and I don't know how to do that on Desmos here. I'll have to learn how to do that. But if you put this into your TI and you put this equation in and graphed it and then looked at the table, you would see at your table, it would give you an error for an answer here. And that's what we call a hole, because it looks like it exists here. It looks like it exists, right? But there's actually a hole or an extraneous solution right there at x equals positive 2. Okay? It looks like I have time. Maybe I have time for one more. If I pause it, I will pause it, and I will put up one more practice problem for you guys to look at. All right, you guys, so I just quickly already factored this out. My original rational function is over here. Whoops, what happened to my pen? My original rational function is here. I completely factored the numerator and the denominator here. I got x minus 2 times x minus 3. If you multiplied that together, you get the numerator. And I simplified the denominator by combining my like terms. And then on that denominator, I noticed I could take out a negative 3, and I just wanted to make sure there wasn't going to be any holes in this solution or any extraneous solutions. So I factored a negative 3 out, and that made my denominator become negative 3 times x minus 1. None of the terms work. There's nothing I can cancel out. So the only number that is going to make the denominator 0 is if I make this x a positive 1 here. 1 minus 1 is 0. 0 times negative 3 is 0. So the vertical asymptote for this rational function is x equals positive 1. Okay? And that's my vertical asymptote for that one. So please let me know if you have any more questions around asymptotes, or if you need help with your practice problems for them.